Relative Gravity Lecture 2. The Thermodynamic Universe.
(1) The void, the birthplace of dimension and time. The thermodynamic universe, universal equilibrium, energy regulation, and the emergent nature of time and space. The cosmos did not begin with form, space, or time. Instead, it originated in what can only be described as the void, a state devoid of structure yet rich with latent potential. Unlike traditional views that depict emptiness as a vacuum, relative gravity posits that the void is a dynamic field where the fundamental transactions of energy give rise to structure. By Orion Carl Daly 2. Cookbook for the Universe, the Transactional Nature of Dimension and Time. A fundamental premise in thermodynamic cosmology is that time and dimension do not pre-exist the universe, but instead emerge from interactions within the void. The first transaction, the most primordial of all, manifests through the principle of opposites. Within the void, the simplest way for anything to exist is through dualistic contrast, hot and cold, dense and diffuse, expansion and contraction. This fundamental duality is the precursor to all emergent structures. Each energetic fluctuation or perturbation in this primordial state generates localized dimensional frameworks, giving rise to spatial and temporal order. In this way, time itself is a property that arises from the cycle of transactions occurring within the void, and it remains intrinsically tied to the evolution of the cosmos. Every event or interaction introduces a new reference frame, reinforcing time as an emergent property rather than a static continuum. Thus, the void is not simply an absence, it is the primordial sea from which time, space, and form emerge through energy transactions. The emergence of the Carnot cycle and the delta phenomenon. The emergence of structure from the void follows a recognizable pattern found in thermodynamic systems, the Carnot cycle. This cycle, which governs the efficiency of heat engines, finds an unexpected but profound application in cosmology. The four fundamental phases of the Carnot cycle: adiabatic compression, ISA, thermal expansion, adiabatic expansion, and ISA, thermal compression, serve as the very basis of dimensional transactions. By Orion Carl Daly 3. Aka, Essay on Relative Gravity to describe the mechanics of the universe. Each iteration of the Carnot cycle within the void represents an evolutionary step in the formation of reality. As energy is compressed, it accumulates density, forming the seed of singularities, localized regions of high energy concentration. When energy expands, it disperses into new frames of existence, defining the creation of dimensions. These cycles ensure that motion remains continuous, preventing cosmic structures from reaching a static equilibrium that would end their evolution. This process aligns directly with the delta phenomenon, the fundamental mechanism of change and iteration across all scales of reality. The delta phenomenon describes how each state of existence inherits properties from its prior iteration while introducing variations that lead to further evolution. This concept mirrors the manifold nature of reality, where singularities emerge, expand, and form dynamic structures in accordance with thermodynamic principles. The formation of the first manifold and the singularity. From within the void, through the interactions governed by the Carnot cycle and the delta phenomenon, the first identifiable entity emerges, the primordial manifold. This is the first recognizable frame of reference and initial distinction between something and nothing. This manifold represents a self-contained energy system, marking the first occurrence of space-time curvature and the first precursor to a singularity. The formation of this singularity is not a random event, but a necessary consequence of the thermodynamic interplay of forces within the void. The singularity is a point where energy density reaches a critical level, creating an environment where energy becomes constrained into an organized framework. This point of concentrated energy, this primordial singularity, sets the foundation for what will become the universe itself. Conclusion: the transition toward universal structure. The discovery of a structured energy cycle within the void leads to the formation of a primordial singularity, a self-contained system of energy and time. This singularity, functioning as the first manifold of existence, becomes the fundamental reference point for all further cosmic development. As the singularity evolves, it undergoes thermodynamic transitions, setting the stage for the grand transformation that will define the universe. This transition leads directly into the next phase of cosmic evolution, the journey from singularity to the Big Bang, a thermodynamic transformation that marks the first great restructuring of the cosmos. By Orion Carl Daly 4. Cookbook for the Universe 2. From Singularity to the Big Bang, a thermodynamic transition. Transition from the void to the formation of a singularity marks the first step toward the structured universe we observe today. However, rather than treating the singularity as an isolated point of infinite density, relative gravity and thermodynamic principles suggest that it represents the first manifold of existence, an entity structured within the emergent dimension of time. 2.1 The singularity as the first manifold. A singularity, as often described in classical physics, implies a breakdown in known laws where gravity and quantum mechanics converge. However, in the framework of the thermodynamic universe, the singularity is not an endpoint, but the first structured frame of reference, a stabilized thermodynamic state that arises due to fundamental transactions in the void. The singularity manifests as an equilibrium point, balancing opposing energy states in the pre-universal field. As a manifold, the singularity becomes a localized system of energy containment, giving rise to the first distinguishable structure within the void. This moment introduces a foundational reference for time, as interactions within the singularity establish a measure of change relative to the void. Thus, the singularity is not an arbitrary point of infinite density, but a regulated state of energy containment, forming the basis for all subsequent cosmic evolution. By Orion Carl Daly 5. Aka, Essay on Relative Gravity to describe the mechanics of the universe 2.2, the Big Bang as a thermodynamic phase shift, rather than an instantaneous explosion from an infinitely dense point. The Big Bang represents a structured phase transition, a thermodynamic expansion cycle initiated by the conditions within the first manifold: compression and energy accumulation. The singularity experiences increasing energy density, reaching a thermodynamic threshold. Phase transition to expansion, following principles akin to adiabatic expansion. The high energy state of the singularity results in a rapid phase shift, converting stored potential into kinetic energy. Carnot cycle in cosmic evolution. The four fundamental phases of the Carnot cycle provide a parallel to the Big Bang's transition from the singularity to cosmic inflation. Adiabatic compression. Pre-Big Bang energy accumulates within the singularity, creating high-density conditions. Isothermal expansion. Energy disperses outward in a controlled expansion, allowing structured formation of fundamental particles. Adiabatic expansion. The universe cools, shifting from high-energy plasma to stable atomic structures. Isothermal compression. Gravitational interactions within the universe regulate the expansion, preventing infinite dispersal. This model illustrates how the Big Bang is not an isolated explosion, but rather a controlled thermodynamic transition, governed by cyclical energy transactions. 2.3 The emergence of structure from energy regulation. Following the thermodynamic shift of the Big Bang, energy flow was regulated into patterns that eventually formed the first galaxies, stars, and cosmic frameworks. Gravitational impedance as a regulatory factor. Instead of an unbounded expansion, gravitational impedance serves to regulate cosmic motion, ensuring the structured evolution of matter and energy. The role of manifolds in cosmic structuring. The first post-Big Bang manifolds stabilize local energy fields, preventing chaotic dissipation. Relative gravity's perspective on expansion and stability. Energy cycling within these emergent structures prevents runaway expansion or collapse, preserving equilibrium within the evolving cosmos. By Orion Carl Daly 6. Cookbook for the Universe 2.4 Conclusion. From Singularity to Structured Cosmos. The emergence of the universe from the void follows a structured thermodynamic process. The singularity represents the first stabilized manifold, introducing a structured reference within the dimension of time. The Big Bang is a thermodynamic phase transition, aligning with principles of energy conservation and expansion regulation. Energy cycling through the Carnot cycle paradigm prevents uncontrolled entropy, ensuring sustained cosmic structuring. As we move forward in exploring cosmic equilibrium and thermodynamic regulation, we see how galaxies, stars, and black holes continue the processes initiated at the Big Bang, maintaining a self-sustaining cosmic system. By Orion Carl Daly 7. Aka, Essay on Relative Gravity to describe the mechanics of the universe 3. The Carnot cycle and cosmic energy flow. The universe operates as a self-regulating thermodynamic system, where the fundamental principles of heat exchange and energy flow determine the formation and sustainability of cosmic structures. The Carnot cycle, a model that describes the efficiency of heat engines, can be extended to explain how energy moves between high-energy and low-energy states throughout the universe. Rather than viewing the cosmos as a linear progression from order to entropy, relative gravity presents a universe that cycles through regulated phases of expansion, contraction, and energy redistribution, sustaining equilibrium across cosmic timescales. The Carnot cycle does not just apply to localized systems, it is the blueprint for how energy transitions shape the very nature of space-time, galaxies, and black holes. By understanding the universe through this lens, we reveal that its structure is not dictated by chaos or randomness, but by an intricate, self-organizing thermodynamic process. The four phases of the cosmic Carnot cycle. The evolution of the universe follows a thermodynamic sequence akin to the Carnot cycle. Adiabatic compression. The pre-expansion state condenses energy into an extreme density manifold, increasing temperature and potential energy before release. Isothermal expansion. The expansion phase disperses energy outward, enabling the formation of fundamental cosmic structures. Adiabatic expansion. the continued dispersal of energy cools the universe, allowing atomic structures to stabilize. ISA, thermal compression. Gravitational forces balance expansion, regulating matter distribution and preventing runaway entropy dissipation. Just as in classical thermodynamics, these phases are cyclical rather than linear, meaning that cosmic structures continuously renew themselves across different scales of time and space. By Ryan Carl Daly 8. Cookbook for the Universe. Cosmic structure formation as a thermodynamic process. As the universe cycles through its thermodynamic phases, galaxies, nebulae, and black holes emerge not as random occurrences, but as the inevitable outcomes of energy regulation. Each of these structures embodies a unique phase within the universal Carnot cycle, balancing temperature, pressure, and gravitational forces to sustain their existence. Galaxies as self-sustaining engines. The rotational stability of galaxies is not accidental. It results from the balance between kinetic motion, gravitational impedance, and radiative cooling. Energy is cycled between the galactic core and interstellar space, maintaining dynamic equilibrium. Nebulae as thermodynamic reservoirs. Nebulae function as stellar nurseries, where localized energy gradients drive nuclear fusion, leading to the birth of new stars. Temperature fluctuations within nebulae act as thermal regulators, ensuring that energy is not dissipated but recycled. Black holes as spatial induction engines. Rather than being mere gravitational sinks, black holes are energy redistribution centers. High energy matter absorbed by black holes is either converted into gravitational radiation or expelled as relativistic jets, reintroducing energy into the cosmic cycle. These structures demonstrate that the Carnot cycle is not an abstract thermodynamic principle, it is the fundamental framework governing the formation, evolution, and longevity of all cosmic phenomena. The first 3 minutes as a universal recurrence. Classical cosmology describes the first 3 minutes of the universe as the critical period in which fundamental forces emerged, atomic structures formed, and the universe set its long-term trajectory. However, relative gravity proposes that this process is not a singular event, but a universal thermodynamic model that occurs across cosmic scales. Every galaxy follows a scaled version of these thermodynamic phases, mirroring the first 3 minutes of the universe. Every supernova explosion represents a microcosm of the Big Bang's initial energy expansion and contraction. By Ryan Carl Daly 9. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. The Big Bang is not a one-time event, but one of many thermodynamic resets that continuously define cosmic evolution. If thermodynamic balance is universal, then the first 3 minutes are not unique. They are an emergent feature of an ever-repeating cosmic cycle. This understanding bridges the gap between microcosmic and macrocosmic scales, demonstrating that the principles governing atomic interactions also dictate the fate of galaxies and the universe as a whole. Conclusion: energy flow as the universal architect. Carnot cycle is not just a model for heat engines, it is the fundamental mechanism through which the universe self-regulates. Whether at the level of a single galaxy or the entire cosmos, the same thermodynamic laws apply, ensuring that energy is neither lost nor randomly distributed, but instead transformed, cycled, and perpetuated in a continuous flow. By reinterpreting cosmic expansion, contraction, and structure formation through relative gravity's thermodynamic lens, as the universe cycles through its thermodynamic phases, galaxies, nebulae, and black holes emerge not as random occurrences, but as the inevitable outcomes of energy regulation. Each of these structures embodies a unique phase within the universal Carnot cycle, balancing temperature, pressure, and gravitational forces to sustain their existence. Galaxies as self-sustaining engines. The rotational stability of galaxies is not accidental. It results from the balance between kinetic motion, gravitational impedance, and radiative cooling. Energy is cycled between the galactic core and interstellar space, maintaining dynamic equilibrium. Nebulae as thermodynamic reservoirs. Nebulae function as stellar nurseries, where localized energy gradients drive nuclear fusion, leading to the birth of new stars. Temperature fluctuations within nebulae act as thermal regulators, ensuring that energy is not dissipated but recycled. Black holes as spatial induction engines. Rather than being mere gravitational sinks, black holes are energy redistribution centers. High energy matter absorbed by black holes is either converted into gravitational radiation or expelled as relativistic jets, reintroducing energy into the cosmic cycle. These structures demonstrate that the Carnot cycle is not an abstract thermodynamic principle, it is the fundamental framework governing the formation, evolution, and longevity of all cosmic phenomena. The first 3 minutes as a universal recurrence. Classical cosmology describes the first 3 minutes of the universe as the critical period in which fundamental forces emerged, atomic structures formed, and the universe set its long-term trajectory. However, relative gravity proposes that this process is not a singular event, but a universal thermodynamic model that occurs across cosmic scales. Every galaxy follows a scaled version of these thermodynamic phases, mirroring the first 3 minutes of the universe. Every supernova explosion represents a microcosm of the Big Bang's initial energy expansion and contraction. By Orion Carl Daly 11. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. The Big Bang is not a one-time event, but one of many thermodynamic resets that continuously define cosmic evolution. If thermodynamic balance is universal, then the first 3 minutes are not unique. They are an emergent feature of an ever-repeating cosmic cycle. This understanding bridges the gap between microcosmic and macrocosmic scales, demonstrating that the principles governing atomic interactions also dictate the fate of galaxies and the universe as a whole. Conclusion: energy flow as the universal architect. Carnot cycle is not just a model for heat engines, it is the fundamental mechanism through which the universe self-regulates. Whether at the level of a single galaxy or the entire cosmos, the same thermodynamic laws apply, ensuring that energy is neither lost nor randomly distributed, but instead transformed, cycled, and perpetuated in a continuous flow. By reinterpreting cosmic expansion, contraction, and structure formation through relative gravity's thermodynamic lens, we uncover a universe that is not winding down toward disorder, but instead sustains equilibrium through perpetual energy transactions. The laws of thermodynamics do not predict a heat death, but rather reveal a universe where energy, motion, and structure are maintained in an endless, self-renewing cycle. By Orion Carl Daly 12. Cookbook for the Universe 5. Universal Regulation. The Role of Energy in Motion. With galaxies, stars, and black holes in place, the next question arises: how does the universe maintain stability over billions of years? The persistence of vast cosmic structures suggests that a deeper mechanism governs energy distribution, preventing collapse or runaway expansion. Gravitational impedance as an energy regulator. Instead of viewing dark matter as a form of invisible mass, relative gravity proposes that what is perceived as dark matter is actually an impedance effect, moderating energy flows across cosmic structures. Rather than being an exotic form of matter, this impedance represents a relational property of space-time, acting as a resistance force that counterbalances gravitational motion and prevents large-scale structures from fragmenting or collapsing inward. A damping mechanism. This impedance functions similarly to a damping force in oscillatory systems, ensuring that rotational and gravitational dynamics do not lead to instabilities. Stabilizing kinetic energy. It prevents galaxies from dispersing their kinetic energy uncontrollably into the vacuum of space. Dynamic equilibrium. It acts as a stabilizing mechanism in the dynamic equilibrium of celestial bodies. Mathematically, this can be expressed as ZR equals 2 plus alpha m, where ZR represents the gravitational impedance, m is the relative mass energy in motion, alpha is a resistance factor that moderates gravitational response. Through this framework, relative gravity provides a mechanism for large-scale energy regulation, ensuring that cosmic structures remain stable rather than decaying or dispersing over time. By Orion Carl Daly 13. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe 5.1 The Galactic Carnot Cycle, a thermodynamic framework. Each galaxy operates like a thermodynamic engine, continuously cycling energy between hot and cold reservoirs in a self-sustaining equilibrium. This follows the galactic Carnot cycle, mirroring classical thermodynamic cycles governing energy exchange. Hot reservoir TH, the galactic core, fueled by stellar formation, supernova and black hole accretion processes. Cold reservoir C, the galactic outskirts and intergalactic medium, where energy dissipates into lower temperature environments. Entropy regulation. Black holes and gravitational impedance function as regulators, redistributing energy and preventing runaway entropy accumulation. By Orion Carl Daly 14. Cookbook for the Universe. The interplay between these thermodynamic states ensures that energy is neither lost to disorder nor concentrated in a way that destabilizes galactic structures. Instead, energy follows structured pathways of redistribution, much like a well-regulated heat engine. 5.2 Motion against cold space and sustained cosmic balance. In classical thermodynamics, an object at rest in an open system will gradually reach thermal equilibrium with its surroundings. However, the universe does not operate as a passive system. Moving toward heat-death motion against cold space is an essential property of cosmic thermodynamic regulation. Kinetic energy retention. Celestial bodies maintain their thermal and kinetic properties by continuously moving through space, interacting with gravitational fields and exchanging energy within their local environments. Relative gravity's perspective. Motion sustains energy distribution, rather than allowing structures to settle into static equilibrium. This explains why galaxies do not collapse inward or disperse outward indefinitely. Preventing total entropy collapse. The dynamic nature of celestial motion, in conjunction with gravitational impedance, ensures that cosmic structures persist in a state of thermodynamic balance rather than entropy-driven dissolution. Implications for the universe as a self-sustaining system. Through this understanding, we redefine the nature of cosmic evolution. The Big Bang does not need to be a singular event, it can be part of an ongoing thermodynamic transaction cycle. By Ryan Carl Daly 15. Aka. Essay on relative gravity to describe the mechanics of the universe. Multiversal interactions may introduce additional Big Bang-like resets at different cosmic epochs. Relative gravity suggests that time and space are not fixed but are continuously being created through thermodynamic transactions. By merging relative gravity, gravitational impedance, and thermodynamics, the universe can be seen as a vast, self-regulating system where energy, motion, and entropy are perpetually managed to sustain structural equilibrium. 6. Expansion, contraction, and the cyclic universe. For much of modern cosmology, the expansion of the universe has been treated as the dominant feature, leading to models where space continues stretching indefinitely or eventually collapses under its own gravity. Relative gravity challenges this view, introducing a dynamic model in which expansion and contraction exist in continuous balance governed by thermodynamic principles. 6.1 The universe as a self-regulating system. Rather than treating cosmic expansion as a one-way process toward entropy, the universe operates as a thermodynamic system, wherein energy flows between states, allowing for structural equilibrium over vast timescales. Expansion as a thermodynamic process, the universe expands in response to energy differentials, much like the expansion phase of a thermodynamic cycle. The outward motion is not chaotic, but follows predictable patterns driven by relative equilibrium, ensuring that motion itself sustains cosmic structures rather than leading to unbounded dispersal. Contraction is a natural counterbalance as energy disperses across cosmic scales. Gravitational impedance emerges as a counterforce, preventing indefinite expansion. At a critical threshold, contraction occurs not as a universal collapse, but as an integral phase of cosmic recycling, a perpetual energy cycle. Not heat death. Classical models predict that the universe may succumb to heat death, a state of maximal entropy where energy is evenly distributed, and no meaningful work can be performed. Relative gravity instead presents the universe as a self-regulating system, where energy continuously transitions between expansion and contraction, ensuring perpetual renewal rather than irreversible dissipation. By Ryan Carl Daly 16. Cookbook for the Universe 6.2 Expansion and Contraction as a Thermodynamic Cycle. This self-regulating motion aligns with the Carnot cycle, which describes how energy flows in an engine to maintain efficiency. When applied at cosmic scales, adiabatic compression, energy accumulates in regions of high gravitational influence, such as galaxies and black holes. ASA, thermal expansion. As gravitational impedance moderates motion, energy redistributes outward, preventing collapse. Adiabatic expansion. The universe continues its outward motion, maintaining structural integrity through conserved kinetic energy. ASA, thermal compression. Large-scale contraction reintroduces energy to the cosmic engine, preventing uncontrolled entropy growth. Each of these phases plays out across galactic and cosmic scales, meaning that the universe is not a single, uniform system expanding or collapsing, but rather a collection of interwoven thermodynamic subsystems, each balancing energy through cyclic transitions. 6.3 Implications for a cyclic universe. If expansion and contraction are thermodynamic properties of the universe, then the cosmos does not require an ultimate end state, whether a final collapse or heat death. Instead, it functions as an oscillating system where energy is neither permanently lost nor stagnated. Cosmic recycling. Expansion and contraction ensure that matter and energy continuously reform, rather than decaying into an irreversible void. Galactic stability. The thermodynamic interplay between expansion and gravitational impedance prevents galaxies from either flying apart or collapsing inward. Multiversal flow. If this process extends beyond our universe, it suggests a network of interdependent systems where universes themselves may operate under similar thermodynamic cycles, regulating energy across a broader multiversal framework. Thus, the universe should not be seen as a simple structure moving toward an inevitable fate, but as a dynamic, thermodynamically active entity, a self-regulating system in perpetual equilibrium. By Ryan Carl Daly 17. Aka, Essay on Relative Gravity to describe the mechanics of the universe 7. Multiversal energy flow. Is the universe part of a larger system? The thermodynamic universe proposes that cosmic regulation is not confined solely to our observable universe. If energy is truly eternal and self-regulating, it follows that it must adhere to a larger framework beyond our current cosmological boundaries. This raises a profound question. Is the universe a closed system, or is it part of a broader thermodynamic continuum, one that extends into a multiversal network of energy flow, exchange, and regeneration? 7.1 The multiverse as an extension of the Carnot cycle. In the same way that galaxies self-regulate their energy cycles, could entire universes be engaged in thermodynamic transactions at a grander scale? If so, this would suggest that our cosmos is not a singular, isolated entity, but one of many universes interacting through a thermodynamic framework that governs multiversal stability. The Carnot cycle, which we have previously applied to the formation and regulation of the cosmos, can now be extended beyond a single universe. Adiabatic compression universal genesis. A universe forms through the compression of high energy potential within a pre-existing manifold, initiating a new spatial temporal domain. ISA, thermal expansion cosmic evolution. The universe expands and distributes energy, forming galaxies, stars, and cosmic structures through thermodynamic balance. Adiabatic expansion dimensional transition. Over time, energy disperses toward new frameworks, possibly leading to inter-universal interactions or the transition of energy into different cosmic states. ISA, thermal compression reintegration into a multiversal system. Rather than reaching heat death, the universe reintegrates energy into a broader system of regeneration, feeding into the formation of new universes. Each phase mirrors the known principles of energy conservation and transformation, but on a scale that transcends our own cosmic domain. 7.2 The role of higher dimensional manifolds. If universes are part of a multiversal thermodynamic cycle, then higher dimensional manifolds serve as the conduits through which energy flows across cosmic boundaries. These manifolds, operating as thermodynamic junctions, would enable energy equilibrium across universes, just as galaxies maintain stability through energy exchange. Entire universes may achieve equilibrium through periodic thermodynamic transactions with adjacent cosmic structures. By Ryan Carl Daly, 18. Cookbook for the Universe. Entropy regulation beyond a single universe. If entropy dissipation is a concern within a closed system, a multiversal framework could allow entropy to be regulated across multiple cosmic states, preventing absolute thermodynamic decay. Relative gravity as a cross-universe regulator. The presence of gravitational impedance may not be confined to individual universes but extend across the multiverse, influencing energy distribution at multiple layers of reality. 7.3 The delta phenomenon and the evolution of universes. The delta phenomenon, which governs the iterative progression of cosmic structures, suggests that universes themselves may evolve and inherit characteristics from prior states. If universes are subject to the same principles that govern the development of galaxies, then the emergence of new universes is not a singular event, but an ongoing thermodynamic process. Every universe exists within a relational framework where energy is not lost but continuously transformed and re-expressed. Singularities that give rise to universes are not isolated points, but energy transition states within the multiversal Carnot cycle. This perspective fundamentally redefines the Big Bang, no longer as a one-time event, but as a phase within a larger thermodynamic cycle that extends beyond our observable domain. 7.4 The universe as a node in a larger energy network. If energy is never lost and always seeks equilibrium, then the universe itself must be part of an extended thermodynamic network of interactions. The application of the Carnot cycle to the multiverse suggests that what we observe as universal expansion and contraction may be part of a larger self-sustaining system, one in which cosmic energy transitions through interconnected dimensions and realities. Rather than a universe destined for eventual heat death, this model suggests an infinite multiversal system where energy is perpetually regulated, renewed, and transformed. This expands our understanding of existence itself, proposing that the cosmos is not a singular creation, but a network of thermodynamic transactions extending beyond any single universe. By Ryan Carl Daly, 19. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. 8. The universe as an infinite self-sustaining system. The thermodynamic universe proposes a radically different view from traditional cosmological models. Rather than envisioning a universe that is doomed to a heat death or eternal expansion, this framework sees the cosmos as an infinite self-regulating thermodynamic system, governed by energy redistribution, gravitational impedance, and cyclic equilibrium. The universe continuously sustains itself through perpetual processes of motion, expansion, and transformation. 8.1 Beyond entropy. A self-renewing cosmic cycle. The classical thermodynamic view suggests that entropy increases over time, ultimately leading to a state where no useful energy remains for further interactions. However, relative gravity and the Carnot cycle introduce a critical refinement. Energy does not simply dissipate into disorder but is instead cycled through self-sustaining processes across all cosmic scales. Galaxies act as thermodynamic engines, redistributing energy between hot and cold regions. Black holes recycle matter and energy, preventing unbounded entropy accumulation. The Carnot cycle governs universal motion, balancing compression and expansion to maintain equilibrium. This cyclical behavior ensures that energy is never truly lost, but transforms and re-expresses itself within the cosmic framework, perpetuating the existence of structures across time. The universe is a dynamic equilibrium of forces. Rather than a one-directional expansion toward disorder, the universe exhibits a self-correcting nature, where energy flow is regulated through gravitational impedance, preventing uncontrolled expansion or collapse. Motion against the vacuum, ensuring that galaxies and celestial bodies remain dynamic rather than reaching thermal equilibrium. The delta phenomenon, which dictates that cosmic structures continuously evolve in iterative cycles rather than following a linear trajectory. By Orion Carl Daly 20. Cookbook for the Universe 8.2 Implications for the Multiversal Framework. If the universe is not a closed system, but part of a larger multiversal energy exchange, then its ability to sustain itself infinitely becomes more apparent. Multiversal interactions could provide a mechanism for energy renewal, ensuring that our observable universe remains an active participant in an eternal thermodynamic cycle. This suggests the universe is not an isolated structure but a node within a grander energy continuum. Singularities serve as transition points where energy migrates between cosmic states. Multiversal transactions regulate entropy, preventing any single universe from reaching a state of total dissipation. 8.3 Key takeaways. Time and dimension emerge from transactions within the void, reinforcing the idea that spacetime is not fundamental but emergent. The Big Bang was not an explosion, but a thermodynamic transition, structuring energy distribution across cosmic scales. Galaxies, nebulae, and black holes function as self-regulating systems, ensuring that energy does not dissipate irreversibly. The universe does not simply expand, it also contracts, maintaining equilibrium through gravitational impedance. The thermodynamic multiverse provides a solution to entropy, ensuring that energy remains dynamic and continuously recycled. 9. Conclusion: a new understanding of cosmic regulation. The thermodynamic universe presents a bold alternative to existing cosmological theories by integrating relative gravity, energy cycling, and thermodynamic regulation. It proposes that motion, expansion, and contraction are not opposing forces but integral components of a continuous process of regeneration and transformation. This model reconciles the paradoxes of traditional cosmology, offering an explanation for why the universe remains structured and self-sustaining rather than decaying into chaos or expanding into nothingness. By Orion Carl Daly 21. Aka, Essay on Relative Gravity to describe the mechanics of the universe rather than an irreversible trajectory toward disorder. The cosmos functions as an interconnected, infinite system of cyclic transformations, where energy flows, evolves, and reorganizes itself eternally. This perspective challenges the prevailing notion that the universe is bound by a single origin or final fate, replacing it with a dynamic, self-renewing framework, one where the principles of thermodynamics ensure the continuous emergence, transformation, and conservation of cosmic existence.